We're talking about counterpoise and grounding and airfield lighting protection. A very, very interesting topic. As I think, obviously, that's why you've joined us today. We've got 63 slides, so we need to get on with it. But I'm very pleased to say that we've got Kevin Burbidge and Tony Coates from the TMS training division will be leading today's presentation. Keith, who may be joining us, has a hospital appointment that he is unavoidable, so he's having a checkup. So he will hopefully be joining us during the course and be available for the question and answer session at the end. So apologies from Keith. You know he'd very much like to be here. As usual, we have very proud to have Mr. Tony Smith, our resident member of the panel, who will also be contributing in the Q&A session. Nick Okoth, who is Managing Director of MARMS in East Africa, and Carl Johnson, who is a consultant with ABCON in North America and a renowned expert in airfield lighting, as is Stuart Ford, who's been a lifetime in airfield lighting, an expert and very, very passionate about our area. So thank you all, gentlemen, for joining us today. My name is Robert Shapton. I'm Managing Director of TMS Systems. And without any further ado, let's get going. So over to you, Keith and Kev and Tony.
To me, Robert.
That's it. So in today's webinar, we're going to basically discuss the contentious subject of earthing on airfields. And I'm going to use the word contentious because depending on whereabouts in the world you are, it is heavily regulated, is the requirements. And these, as I say, they differ significantly throughout the world. And therefore, today's content provides just a general overview. And therefore, you need to take your local electrical regulations into consideration to address the needs of your systems. So let's get down to it then. So what is an earth? Well, essentially an earth is the conductive mass of Earth whose electrical potential at any point is eventually taken as zero. It is also used, as I say, as a reference point for voltage and the fault path for electrical fault current. So let's have a look at the earthing on airfields. Now, hand over to Tony.
Right, well, the first thing that we need to do is what is the purpose of earthing an AGL circuit? And basically, as far as we're concerned on our side of things, and we will highlight up differences as we go through things, the purpose of earthing an AGL circuit is to ensure that the secondary side of the circuit is maintained at the same earth potential. Now, it's an interesting one, this, because straight away the FAA have different views on this, because the secondary side of the earth circuits over here in the UK, we have on the series circuit transformer, we have an earth tag on the secondary side, whereas the FAA don't. So straight away, we're looking at there are differences no matter where you are, as Kevin said. Now, in order to put earthing onto an AGL circuit, the requirement is it should be done using a reliable and continuous equipotential bond. Earthing circuits should be installed in a minimum of, over here, 6mm squared cable, and this is non-insulated if it's buried in the soft. If insulated cables are installed, then the system requires earth rods, generally no more than over here 300 meters. In America, we were discussing earlier on, depending on whether it's the FAA or USAF, they have 500 feet and 2,000 feet as their requirements. So there are various differences. And speaking with Nick, they've got 150 meters that they work to. So again, as Kevin said, every country has slightly different requirements. And so the knowledge of the local requirements is essential and key. So there you go, a nice little earth rod in a pit somewhere. The earthing circuits can either be a radial or a ring circuit. If it is a radial circuit, then there have to be test points, and these will be set in line with what the designer specifies. The designer will specify where the test point should be. Maximum resistance of a system, ideally 6 ohms. It should not exceed 6 ohms. So therefore, you look at the length of cables that are going to be run around. You're obviously going to have to create a matrix system of cables in order to create the parallel paths to drop the resistance down. So grid and mesh connections are required. Now, any of these connections have to be done using clamps. You can't crimp them or anything like that. They have to be using clamps. And the earth rods, which are also used as the test points, should be easily accessible. And ideally, they should be in either the pits, if you got them, or in earthing pits. So here we have a nice picture. This is taking the way we work things. If you look, you've got secondary terminals on the SCTs, and these are connected to an earth bar within the pit. So pits should be equipped with an easily accessible earth bar to which the secondary circuit transformer earth studs are connected, as shows there. The earth bar is up in the top corner and it's easily accessible. Elevated light fittings may require bonding back to the earth bar. A rule of thumb generally tends to be that if they get towards the 2 meter, the mast gets towards the 2 meter height, then they will require a bonding. All initial testing of earthing systems should be carried out before any backfilling of trenches. Obviously, if there are problems, it's a lot easier to rectify them if you haven't backfilled the trench. So, and an AGL earthing system is required for every primary route, not every primary circuit. And by this, you mean it may be that you have 5 different circuits running in the same trench. You do not need an individual earthing circuit for each one of those circuits. Then that trench, one earthing circuit would be adequate as long as it connects with all the relevant points. And the last thing that comes into play is the testing of earth circuits. Now, Kevin, a bit later on, will go into detail on how testing is carried out, but realistically, testing should be carried out at least, and I say at least, once every 12 months. The results should then be compared with the initial installation results and also any previous tests, in order that you can see if there is any degradation on the circuit and how the general circuit is holding up. Now, with regard to testing, the easy way is using a clamp. And again, Kevin will go into more detail on this a bit later on in the talk. Oh, right, I've lost my page. So the other thing that comes about is in the title are counterpoise systems. Now, counterpoise systems are basically a form of lightning protection system, and as such come under slightly different regulations and requirements compared with an earthing system. They're designed and installed to protect AGL installations from lightning strikes. And one of the things that is apparent with regard to this is the responsibility and the knowledge of the designer of the circuits. The designer is responsible for carrying out the necessary calculations to ensure that adequate protection is provided to the primary circuits that it is protecting. Now, in the UK and Europe, it's BSEN or EN 62305 that details all the calculations that are required to be carried out. But the designer has to start off realistically with the resistivity of the soil, because again, this has a major factor and a major bearing on what size earth rod is going to be installed. So there's a lot of work that needs to be done. And one of the things that came about in conversations earlier with someone who is involved in design is that he actually sees his role as educating the client. So counterpoise systems over here, we use 16 mil squared cable, copper cable. It is non-sheathed. It is bare cable. And the designer will have this. If you take the bottom line on that triangle as being the bottom of the trench, and the top point as being the ground level of the triangle, then you'll see that the counterpoise cable is set at a distance of 150 millimeters from the top of the surface level. And counterpoise systems were originally designed for use on masts, radio masts, and so they create a cone of protection. And this is what the basis of it is. So when a designer is doing his calculations, not only can he tell you the optimum depth, but he can tell you the maximum depth and maximum width that counterpoise system will actually protect. So, as I say, the designer has a lot of responsibility in this side of things. So back to the normal picture of the counterpoise system, how it runs round. The ideal resistance for the entire system should be between 3 and 6 ohms. So again, we look at the situation, it's going to require a series of matrix links to create the parallel paths to ensure that the resistance is low. The resistance under no circumstances should generally exceed 10 ohms. It should not exceed 10 ohms. And so it's therefore critical that these additional paths are put in to bring the resistance down. So if you have a situation, for example, an approach system, it may well be that you want to run a spur. You can run a spur off a counterpoise system. However, the connection, as with any connection on a counterpoise system, has to be done with a clamp. So, and we're looking at something like this, which uses the skin effect from the circumference of the cable to ensure greater continuity and less resistivity between the two cables. So the other thing with regard to a counterpoise system, and again, this is a variation in UK and Europe, or any location where there is a secondary stud on the transformer, which is connected to an earth bar. If you have that situation, you do not connect the counterpoise system to the pit earth bar. Now, the FAA, because they don't have the secondary stud on the transformers, they actually connect their counterpoise system into the earth bars in the pits. Whereas if you have the secondary earthing side of things on the SCTs, then you don't. So what else do we need to know? Counterpoise system should be a continuous cable. Ideally, yes, it'd be wonderful if we could, but take a heck of a big drum of cable to go all the way around. So therefore you can have joints, but again, it's got to be using the clamp. Where joints are connection and connections required, ideally, the best place to do these is an earth rod, which you can utilize then as a test point. And earth rods, again, ideally, should be over here, no more than 300 meters apart. So the other thing that comes about is protection of metal equipment. Where a counterpoise system is installed, all metallic equipment not normally connected to AGL earthing system should be bonded to the pit earth bar. So this could be the PAPI stand, the legs on the PAPIs. It could be the light fittings, be them inset or elevated, and the signs. So it's not just a simple case of running a cable round. There's a lot of things to be looked at. And then again, the testing, which Kevin will go through, a minimum of once every 12 months. And again, in order to gain from those results, they need to be compared with previous results. At the end of the day, a one-off test will tell you yes or no. It won't show you the trends, it won't show you the history. So therefore, always compare your tests with previous results. So I'll hand back to Kevin now with regard to how that testing is carried out.
Okay, so as far as your testing is concerned, as I say, the majority of the recommendations from various countries is that the testing is done every 12 months. In reality, you're actually better off testing every 11 months, which then gives you a rotational of the readings. It's extremely difficult at the best of times. If you take an average airfield, you're going to be looking at several hundred earth spikes to go around. So it is a really labour-intensive task, is this. So as I say, splitting it across different months, it allows us to build the trends of the what's actually happening with the soil. So if we have a really particularly dry spell, obviously our resistances are going to be extremely high, whereas if it's wet, it's going to be extremely low. So it gives us a benchmark, if you like, and we can see overall what is happening to our systems. When it actually comes to the testing of it, we can split this into basically 4 main methods which we could adopt. Now, some of the methods are more reliable than others. The most reliable method, as I say, is the four-pole tester, which can be jointed out, and we can use it as either a 3 or a 4-pole terminal tester, as we've got in the diagram. Essentially, what we're looking at there is we've got an electrode under test, we've got a voltage spike, and we've got a current spike. Now, the current spike is situated usually about 30 meters away from our standard earth electrode that's under test. Now, this can't always be achieved, especially if it's near an apron, and because the last thing we want to do is knock holes in the pavement. So it may be that we look at a slightly different method for testing, which I'll come on to a bit later on. But the distance is proportional to the length of the earth spike under test. Now, when we design our systems, we've put we know what length of earth spike we've got in the ground. Majority of people tend to use either a 2-meter spike or a 3-meter spike. In the example that we've got on the screen, this is a 3-meter spike, and the first current electrode is actually situated 30 meters. So it's roughly a 1 in 10 ratio that we've got. The central point, which is a voltage reference spike, we move that forward and backwards by 3 meters each time, and we take 3 separate readings. The idea behind this is we can get an average of our earth resistance on our electrode, and it gives us a good understanding of what is actually happening. If the spike, the voltage and the current spike are placed too close together, this will generate overlapping fields, and it will give us false readings. The other thing to bear in mind, when we test an earth electrode, you do need to disconnect that earth electrode from the system. Otherwise, you will get seriously strange readings. So we mentioned the clamp, and we showed the photograph of the clamp. Now, some countries don't actually have clamp meters. They are relatively expensive. They're about 1,400 UK pounds, about $2,000 to buy. The one in the photograph is actually made by a company called Mega, which is actually American owned. The device does need a reference point in order for it to work correctly. So all we do is we put the clamp around the cable next to the earth electrode and we take our reading. But we do need to make sure that it is referenced. If it's not referenced, then we won't get the readings that we desire. So this is basically a network system. The green blobs in the middle represent earth electrodes, and essentially you're going around each of the individual electrodes and you're taking a reading. The clamp meter basically injects a voltage and a current, and it will give you an approximation of the resistance of your earth electrode under test. It is fairly accurate. Having tested both conventional 3-terminal and then used a clamp, the readings are pretty good. They are pretty accurate. Moving on. So the next method that we could use, method 3. Method 3 basically has a current clamp. We still have our voltage spike and current spike, but this time what we do is we attach a current clamp around the earth electrode. This minimizes any false readings that we may get within our system, and that we can then just take a reading straight off. We don't need to take multiple readings, so it's saving us a little bit of time. Also, our distances are significantly reduced as well. So the third method we could use is to actually just use 2 clamps, and again, by using 2 clamps, it minimizes our field effects. But this time we can actually leave the entire network all connected, and it will give us a good approximation. As I say, we're seeing this type of test used more and more where we've got the 2 and 3 pin meters. And finally, we could actually use a loop impedance tester. It's not something I would recommend out in the field. It's a little bit impractical to use. It's okay if your earth bed is next to the B center, you've got an electrical supply within the B center, but it's not a method I would recommend, certainly for an airfield. So at this point, we are actually going to go to Q&As. We've deliberately not gone into extreme depth with this because it changes from country to country. So we can only sort of give you a broad overview of earthing systems.
Right. Well, thank you very much, Kev. Thank you very much, Tony. That's very interesting. As I say, it's a big topic, but as there's an introduction, it's a very important topic to you all, and I'm sure it will raise an awful lot of questions. Just so as you know, when we're for next month, just say next month we're talking about managing visual aids compliance in the 21st century. So really, you know, the whole story from moving on to fix on fail to block change right the way through to a discussion about the potential of AI to help you optimize the management of your airfield visual aids. So that will be the next topic on the 28th of May. So I hope you can make that. But coming back to the matter at hand, if we'd like to go now to the panel, we'd like to take your questions. First of all, I'd like to welcome Keith. So obviously, the fact you're here, that's a good sign. So the hospital let you out. So that's always good. So welcome back, Keith. I'm glad you could.
Thank you.
And so now if we look at the questions we have here, I have a first question here. Does it mean that CP wiring is a complete separate system than the earthing system, which connects the earthing bars in the pits with rods, luminaires, earthing lugs on the secondary side of the transformer? So we're talking there about a separate counterpoise system to the actual airfield lights.
This again comes down to where you are, because the counterpoise system over here is a totally separate system. However, as I said, with the FAA, because they don't have the secondary connection on the transformer, they actually link the counterpoise system into the earth bar in the pits. So obviously they have, to a certain extent, a combined system, whereas over here they are two separate systems. So realistically, this is one of the things where, as I say, this is where the designer earns his money, by knowing exactly what is required in the area that he's working.
Okay. Yes, so that it's I think, and also in Carl, what is the custom and practice in North America?
In North America, we would have the counterpoise system that would be attached to each light base. This is for an equal potential system. You have a counterpoise attached to each light base. There'd be a bonding jump between the light base and either the fixture or the base plate for the elevated fixture. Counterpoise would be run above the duct and go all the way back to the vault and tie into the vault grounding system. And from our perspective here in the States, the output of the constant current regulator is an ungrounded system. So even if a ground in the output of the regulator would be in abnormal condition, and the regulator is designed to pump 6.6 amps of current from one output lead of the regulator to the other output lead of the regulator. It does not go to ground. It's not looking for ground unless there's a complete circuit there. So any current that leaves the regulator on one lead must return to that regulator on the other lead. We don't use it as a safety ground, or don't call it a safety ground, because again, the regulator is designed to pump 6.6 amps through the circuit. All it takes is 10 milliamps or 20 milliamps to kill an airfield electrician. So there's nothing really safe about the grounding or bonding on it. It is a lightning protection system.
Right, thank you. And Nick, what is your experience in your region? You're on mute. You're muted.
Now, in my region, as well as in many parts of the Middle East, where we have done the design and installations of counterpoise systems, we realized that the secondary or the transformer part of the system is not connected to the counterpoise. Rather, it terminates in the copper bar, in the AGL pit. So this is quite different to the system in the USA and the FAA system. So depending on the region and of course on the national regulatory authorities, it determines how it is about the universal system, where it's applied mostly in the Commonwealth systems, is that in the field, we do not connect the counterpoise systems to the fixtures and the secondaries part of the transformer, but rather it ends or it is terminated in the copper bar, as well as in the 150 in the 150 meter gap, where we have the prefabricated earth pits. You ground it and then you terminate to the earth pit and then you move on to the next. But the secondary part of the fixtures, as well as the transformer studs, these ones normally are run with the yellow-green. Normally, I think they are 4 square millimeters. So somehow this answers the question which was asked in the panel, whether the counterpoise and the grounding system are different. Yes, they're different, because when you're grounding the secondary part of it, it does not form part of the counterpoise system.
Thank you, Nick. It is, as a non-electrical person, it is quite surprising to me that the differences in local regulations, given that this is a matter which is common to all airports, you would think I would have expected more uniformity. What do you think, Keith?
Well, I think the introduction of the LED technology into the AGL world changed the thinking associated with the earthing as a bonding system. For example, the LED itself is an electronic component, where of course the incandescent lights are not, etc. So there is the difference between bonding of the primary circuit and bonding in the secondary circuit. One of the things that we have to appreciate also is that with Seward and Carl, they will confirm that their base units are metallic in construction, whereby in the international theatre, and most countries outside the North American influence or the US influence areas, then the base units are a magnesium alloy, of some description, and the light fixtures themselves are an alloy. Now, alloy is basically a non-conductive material, which of course then negates the requirements, generally speaking, to need to have a earthing network from the light fixture back into the transformer pit, etc. But of course, the LEDs with the electronics in the fixture has changed that scenario. So, as Nick has already mentioned, and as Tony and Kevin has said, we do have the counterpoise earthing network, and we do have an earthing network. Generally speaking, and the international theatre, when we have an earthing network, it is definitely not a counterpoise earthing network, because the cabling is routed differently. The size of the cabling is differently. In the international network, to have an earthing network, then the standard, whatever the national standard is, 1 ohm to earth or 10 ohms or 25 ohms to earth, wherever it is, then however you achieve that, it doesn't have to have earth rods. However, that is the normal method of achieving a zero potential. But when it comes to a counterpoise earthing network, which is principally for lightning protection, then we definitely need to have those earth rods. And those earth rods shall be installed, as Kevin Tony has said, here in the UK, no greater than 300 meters apart. But when you have a counterpoise earthing network on the international theatre, generally speaking, there is no need to have a second earthing network. The counterpoise earthing network can act as that bonding network. So there are these variations, as I think everyone is alluding to here, but as you quite say, Robert, one would think there is standardization, but the standardization that exists associated around the world, it is just not there. So we have to take due consideration of local standards, local regulations, which again, where Nick has alluded to, it comes back to design, eh, Nick? Yeah.
Yeah.
So is being able to be familiar with the local requirements.
And
A big subject.
Yes, and we had this discussion earlier before the seminar in preparation, noting these differences and talking to Carl in particular. This is where having a competent, well-trained consultant is absolutely essential, because in the case of Carl, he's explaining that there are some airports that might adopt a standard that could be optimized by let's say having reducing the spacing of the earth electrodes, and certainly in his designs he may seek to optimize the result, provided it's within the regulations, of course, and that's what a good consultant will do. So looking at the questions,
can I just jump in there before we finish on that, Robert?
Yes.
I mean, for example, we've spoken about the cabling for that earthing network, for counterpoise earthing network of 16 millimeter square plus cross-sectional area plus, or for the earthing cable of something like 6 millimeter cross-sectional area. In some airports where they have high electrical activity, then that counterpoise earthing network is not just a single cable, it is a network above the primary cabling system. So it's a grid system.
It's funny you should mention that, because Zuba on the call today has specifically asked, how is the size of earthing cable decided? What is the recommended size? at secondary size. So what is that? So do you know how we've arrived at that sizing? Is it universal as well?
No,
Probably
So-
not.
no.
In the States, the FAA's minimum requirement, I believe, is a 6 currently. It is fluctuated between an 8 and a 6 and a 4 and a 2 over the ages. Historically, a 6 has survived, the 20, 30 years after they dug it back up and it was still there. What I've started doing is I go to a number 2, which is the American wire gauge. The lightning protection standard has a class 1 provision for structures less than 75 feet and a class 2 for structures higher than 75 feet. A class 1 structure, which is what our signs or anything else on the airfield would fall under, approach structures, that kind of thing, would all be less than 75 feet. And the standard American wire gauge size closest to a class 1 conductor is the number 2 AWG. So that's, from my perspective, the default size to use for any counterpoise system here in the States. And the FAA allows us to increase the size based on lightning activity.
Okay, thank you, Carl. And then if I'm looking, just going down the list, there's a number of questions coming in here. Derek asks, with regard to earthing of approach lights on high masts, would the panel recommend they are earthed potentially attracting lightning to your circuits and into the transformer pit? Or is it better practice to leave the light fittings that cannot be touched by hand unearthed? Who wants to take that one?
Are we in the UK?
I can tell you that lightning is not attracted to a grounded object. Lightning decides where it's going while it's still 50 meters in the air. So whether an item is grounded on a mast or not grounded on a mast, one of the historical interesting things was the Royal Navy was losing the mast on their sailing ships. This is back in the 1700s, 1800s. And they'd be in a storm and the lightning would strike the mast on the sailing ship and basically destroy the mast, explode it. And as it turns out, everyone except for the British Navy started putting air terminals on their mast. The British Navy would not do it for another 30 or 40 years because that colonialist rebel, Benjamin Franklin, is the one who discovered the air terminals. And it took the British Navy another 30 or 40 years to start putting air terminals on it. The point being is that mast sticking up in the air was a big, tall stick of wood that had no conductive properties whatsoever. And that's what lightning attached to. So whether your object is grounded or not grounded, lightning is coming to Earth in leaders, and the leader will pick the least resistant point. And so it's grounding an item or installing a lightning protection system does not attract lightning to it.
Can I just interact there? One of the aspects in one of the international airports, hub airports in Asia Pacific region, they had some lightning strikes on their approach masts. And what they have done is to fit a completely separate lightning arrestor system for each of their masts. So they have basically a conductive aerial, shall we say, sticking up from above their approach masts, and then with a solid bar to a ground rod into the ground for each of the approach masts. And that's something which has been adopted and trialed and is installed in an international airport in the Asia Pacific region. It's the first time I personally had seen that, and I was asked to make comment on it around 2 years ago. But just as an explanation, it's still the same concept that everywhere is slightly different.
It's a chapter 4 in 780, what we refer to as chapter 4 protection system with an air terminal and a down conductor. and it would be kept separate from any ground systems within your approach lighting.
Yes.
Okay, thank you for that, gentlemen. Charbel,
Can I add in one thing
oh.
on that? Sorry, before. In the UK, if you have a counterpoise system in, there is a requirement for your masts to be earthed back to the pit, to the earth bar in the pit. That's what the requirement is, realistically.
okay, so again, this is just a reminder to everyone. There are different customs and practices in each nation state, and it's important that that you're familiar with those standards and compliant with your local requirement. I guess you can always go further than the local requirement, but you can't go less than the local requirement. So you need to be aware of what those are. Charbel has asked, is it, and apologies if I get pronunciations wrong, but is it recommended to weld the cable to the earth rod or use a clamp? What if the earth rod is direct buried with no inspection pit? Gentlemen, who wants to take that one?
First thing is that the requirement is that a clamp is used for earthing systems and also for the counterpoise system. Clamps should be used. That is the requirement. Secondly, the general requirement is that earth rods should be easily accessible for test and inspection purposes. However, I think we've all come across situations where there's a load of tarmac or paving slabs or whatever being put over them after the event. But ideally, they should be available for both test and inspection, easily accessible, to quote, and realistically, any connection of an earthing cable should be using a clamp.
Thank you for that. That's clear.
In
Now,
the States, it's an either or.
I was just gonna. Well,
this again comes down to it, and this is the nice thing about this, and where you're on here as well, Carl, is that we're seeing the different sides, the different things coming up, and as Keith's also said, there's different aspects and different requirements everywhere.
Yeah.
It's nice that we're getting this sort of cross section of information.
right. So I'm going to ask a general question for Tony and Seward here, who've seen the development of the standards over these areas and also the consequences. And I'd like to know your thoughts on the development of the in earthing and counterpoise over the time since the standards were developed. Are we what has changed, and do you think we have optimized? Do you think we're optimizing our practices? And in particular, because I note that there doesn't seem to have been much changed here, yet there's an awful lot more technology available to us today. Is there an opportunity to simplify or improve or in some way do something different for the benefit of airfields? Seward, what do you think?
There's a lot to think about there.
Sorry.
That's the biggest thing I see, regardless of the system, is to verify that the system is operational. And we talk about the transformer secondary ground and so forth, and we go on for months or years, and we never see that system is adequately functioning. And so I think we've got several approaches here, and maybe what we could use is something that's more automated and something that's more easily to assess than what we do now, because I think in many instances, we just don't check what we've got. And have we made progress? Probably, but I'm not exactly sure about that. Carl can comment on that maybe better than I could, but it's slow progress, because when something is not right before us to check and we're really convinced that it's got to be checked, we don't check it. And it takes action before we get alerted to it, and then many times it's too late.
I would agree with you there, Seward. I think the key issue you said, do we test? Do we actually test whether we have got earths? Now, Tony indicated in the UK, clamps are used. Clamp method, there are both methods used internationally, welding and clamping. Welding is a securer method, providing the welding has been done correctly with the suitable tools, etc., etc., etc. You know, however, the clamp method tends to get corroded, and when you get corrosion, the environment that the equipment lives in, then unless we are testing for the correct earthing, that is to the resistance to earth, whatever the national standard is, then we don't know whether or not that earth is correct. So welding and clamping, both used, but it's testing. And Seward, I would 100% agree with you. It's the testing that is checking whether or not we have an earthing network, be it a counterpoise or a bonding system.
So Keith, would you say you can't manage what you don't measure?
I think you've said it in one, Robert.
I heard that somewhere. And of course, keeping records and monitoring the trends are equally important. So that's where an airside CMMS is very important to you. So you have the information and present it in a useful way, so you can use it proactively to manage and optimize the outcomes. So Tony, you've had a few seconds there to think through that. I think we call it a hospital pass a moment ago. What is your thought on the topic?
It is an area that in all my years of work and so on, very much this was over to the electrical engineers. It wasn't an area that we did any development work on. We, if you like, passed the buck to the installation people. We didn't get involved in that at all. I really got nothing constructive to say. I'm finding it a very interesting discussion.
Good. Well, thank you. So and Carl.
As far as coordination and growing standards, the FAA has a method of providing information or comments on their advisory circulars in the back of the advisory circular. So there are ways of bringing things before the FAA. The lightning protection and bonding took a number of years to get it revised and updated to accommodate what I consider proper bonding, grounding, and lightning protection for the American systems. And as you said, you can't manage what you don't measure. And I guess it depends on again, you're back to the authority having jurisdiction. I mentioned when we were practicing that's the authority having jurisdiction is the they that gets blamed for everything. But the authority having jurisdiction, the folks that are actually in charge of the airport, having a good proactive maintenance system makes all the difference in the world. It can't be top down or bottom up. It's got to be a combination of both in order to have an effective maintenance system. Good.
And that's something we'll be talking about in our next TMS Tuesday. I have a question here. What is the reason of covering gravel on the ground cables? I don't know if anyone here is familiar with the practice and understands why it is. It's certainly not something I'm familiar with, but do we know why we cover the cables with gravel in particular?
Is this actually inside a trench or is it at the top?
It's not clear. The question is not clear. Is it? Because if the person asking the question could, it's an anonymous question. Yeah. If you could expand on exactly what the nature of the gravel covering is.
My thoughts on that initially would be if it's above the cables at the base of a trench, it's rather like we put sand in, so that when you're digging down, you come to a layer which is different. So if you're digging down, you then get to the gravel, hit the gravel, and you know that you're close to the cable, so you don't force your spade straight away through it.
All right, practical, very
Yeah.
practical. So Raymond in the Netherlands has pointed out that in military air bases, they only have earthing systems and no counterpoise wiring. So that's just the local practice. And again, it does differ. We've spoken about differences, national differences, and certainly in North America is somewhat more different than the rest of the ICAO world.
I could throw out, I'm in Florida, so the majority of the airfield lighting systems in my area are exposed to heavy lightning.
Yes, so
I don't know what the
I have a
lightning
question.
activity is in the Netherlands. If it's a light lightning activity, that could be why there's no counterpoise system. It may not be a necessary expense for them.
right. Well, I think there is a generic term, the Low Countries, possibly that. I don't believe Netherlands is noted for heavy lightning storms, but I'm sure there must be some. But yeah, that could be part of the answer. Another anonymous question. ICAO ADM Part 5 allows the counterpoise system to be used as an earthing system. We believe it is impossible to keep the two systems separated under lighting conditions or lightning conditions. It says lighting conditions. Certainly we talked about earlier, Carl, you said in North America, in US in particular, they are linked together. And we discussed it. In fact, we discussed before the webinar that in UK they're not. They're kept separate, and the reasons why that might be. Kev, perhaps you could.
Yeah, I mean, wherever possible, we've always tried to keep the two systems separate, mainly because you've got the potential for there's high voltage flowing, which can, as I say, potentially damage the equipment in the B centers and that type of thing. As I say, I've seen in numerous occasions where we've had obviously surge protection devices fitted on our systems, but then you look at some of the USAF systems and they refuse to have surge protection fitted within the B centers. Again, we're trying to keep our earth beds separate as well, wherever possible. It's a minefield, and it differs from country to country. It really does.
On the international theatre, generally speaking, if you have a counterpoise, there is no need to have a separate earthing system.
Thank you, Keith. Next question comes from Ilya. There are pros and cons. From my experience, it was sometimes dangerous, but anyone can have. Does anybody have an idea for the installation of AGL, of the surge protection for AGL systems in the field, mostly in Africa? For me, it is most dangerous. It's the most dangerous part. Equipment installed in Airfield in terms of personnel safety as well as installation. We have degradation of isolation values. This is concerning the risks associated with these installing these systems.
Yeah, I think he's talking about the low IR values, and then the danger that it poses to the electricians who access these fixtures in the airfield. A lot of practices, I think, are not well supervised. You find, I think this narrows back to competency and training. You have operators or even regulators having oversight of technicians accessing the airfield, whereby the proper isolation method has not been undertaken. And number two, the cabling system, majority of the installations, I think in the sub-Sahara, they're doing either direct burial, maybe because of the budget constraints, they don't do this robust ducting system, whereby even if the airfield is submerged in water, you have the IP ratings of the transformers and maybe the smart switches somehow it makes it safe to work there. But in many cases of this, when you have the cables probably are old, and then the electrical or the mechanical integrity of the cables are ripped off, and then couple that with the rains, and then you have people accessing the air sites. And of course, this has introduced the weaknesses in the AGL system, and this heavily impairs the IR readings. And the moment the IR readings go down below the minimum required levels, either if the CCR does not shut down, then it's going to shock the electrician. So these are the prerequisite issues that have to be addressed before they allow technicians or electricians to access fixtures in the field.
So
I think here then, Nick, I think you're quite right in what you're saying, but the element of this question is associated with low insulation resistance values, and that brings us to to another subject, of course, that we've already dealt with, and rather than just the earthing network system. But the key issue is that to allow anyone near an AGL system that is an unqualified electrical person is fraught with danger.
But yes, exactly. And but I'm getting from this that the how you implement an earthing system can compromise the insulation resistance under certain circumstances.
I think how you install the AGL system can compromise the IR values.
I think the whole thing with the IR values, and it's a personal bugbear anyway of mine, or personal annoyance of mine, is that the majority of places tend to work on the principle of minimal testing. The regulatory bodies say that the IR should be tested twice a year. So it's tested in March and it's tested in September, because the weather's generally quite nice at that time of year. Realistically, what benefit is it to you? You're not testing in different weather conditions. You're not testing, in the extremes. And unless, as I said earlier, with any test results, unless you compare them back historically, you won't be able to tell whether there's any degradation or not. An AGL circuit, as I said previously, is not designed for personnel protection. It is potentially a lethal circuit. It's better to kill one airfield electrician than to have a plane crash. That's what the CAA say. So, it's a case of, it's there for a purpose. And I agree with Keith that adequately trained and responsible personnel working on them is the key issue, because if you're not aware of what the dangers are, you can't react positively to ensure they're not the danger.
And the question also addresses surge protection. For every lightning arrestor you put in that primary series circuit out there, that's another parallel resistance to ground. So that has a direct impact on the insulation resistance value of your airfield lighting circuit.
Right, thank you. I'm just trying to pick out. We've got we're running short of time here. A statement here. IEC 61820 1-2-2025 fundamental principles. Just a statement of fact. Particular requirements for series circuits. This requires earth electrodes where provided to be measured. The requirement is to earth as per local regulations. I think that's as we've said. So yes, thank you for pointing that out.
I think you also a thing here, Robert, is the IEC standard 61820-1-2 is actually basically a draft document at this moment of time, and it is a new document where the IEC, with the Technical Committee 97, are actually merging many of the other AGL IEC documents into a new series of 61820, and not many people know that. So, and I think that's the fundamental message I'm just giving here, is that the IEC 61820 will become, I understand, the all-embracing IEC document, which covers most of the aspects associated with AGL as technical specifications in the future.
Yes.
Good news.
That's interesting you mentioned that, because I think could be a topic for future. It would be good for the audience of people here, but the nature of you being on this webinar shows you have a high active level of interest in airfield lighting generally, but you have your specialist interests, but also that you're passionate about the topic, and as such you would be wanting to know about what's coming, and you may not be aware of these standards under development. It would be good to know what's coming, and it would also be good in many cases to be able to contribute to those processes, because I think a lot of you know an awful lot about these topics. So we could potentially, guys, do a webinar on what's coming, because I know, from the FAA this week there have been discussions about development of future maintenance standards, about making photometric testing mandatory, about work that's going on the subject from our last webinar, torque management and revisions to the standard there, the escapes my memories there, 83A standard. So looking then to the next question, which is better, ground rod or ground plate?
For installing rods.
Yeah.
For second-hand scrap value, if they're copper, plates. No, for installation purposes, rods are obviously a lot easier. If you're using ground plates, the thing with using a ground plate, generally over here, they're just under a meter square. They come in either copper or cast iron, owing to the fact that copper is generally removed from site. I'll put it that way. They tend to be cast iron. They have to be mounted vertically, so therefore you've got to dig down the best part of a meter and mount them vertically. So with regard to the actual effectiveness, yes, a plate is slightly more effective, but there's not a lot in it. Being quite honest, there's not a lot in it.
So I'm taking from that, for practical reasons, a ground rod would probably be more effective.
Yeah, the thing about it is, if your reading's not right, you can always add in additional rods.
Yeah.
So but for practicality and for ease of installation, I would prefer to install a rod than a plate.
That would also follow economics, because economically it's probably cheaper to put in a couple of rods and drive those than it is to buy the plate. The plate we typically would reserve for somewhere where we have shallow soil on top of rock or something, and you can't drive a rod, then we'd excavate for the plate.
Good
But
point,
typically
Carl.
we'd use
Yeah.
the rod.
Good point. Yes. So
I-
go on, Tony.
A question just occurs to me. Are we assuming always that beside the runway we've got soft? Because I can think of one airport in this country where the manufacturer, the installer, when I said to him about burying the cables, he said, "Oh, there's no trouble with that." I pointed out that there was an inch or two of soil, and then it was solid granite. So driving a stake into solid granite isn't going to work very well, is it?
Now, what we can do there, though, Tony, is we can actually put boreholes in and then make a slurry up using something like bentonite and cement, and actually concrete the rod into the granite rock to form our earth bed.
Thank you.
Robert, can I just interrupt? I saw there's two comments made about my comment of the IEC 61820 as being a draft. Yes, I would agree with the comments that have come in. It is now a standard. It has been released. Right? So it has been a draft until recently.
Okay, thank you.
Yes, thank you.
Right. And comment here. If we test 11 months every 11 months rather than every 12, does that not impact on our ability to trend analysis properly? I think one for you, Kev.
Well, the thing is, if you're doing it every 12 months, you're getting the same ground conditions. So therefore, you're looking at exactly the same readings. Essentially, what we need to do is have a trend across the seasons so that we actually understand what is actually happening sort of in the dry months against the wetter months. Because it might be that during the drier months, our earth resistance is way out of spec, and that is when we probably most need it. So it means that we can then reassess whether we need to actually increase our earth rods within our system as well.
The other thing on that is, and it comes back to something I said earlier, the requirement is at least once every 12 months, at least. Not mandatory once every 12 months, it is at least. So you have to do it at least once. Why not do it once every 4 months, once every 3 months? You know, if you've got the time to do it more often. Get yourself a history, get yourself a trend with regard to the environment at the time, weather conditions, things like that. So yes, everybody tends to work on, the regulations say we do it once a year. So we'll do it once a year. But in order to gain a true history, it needs to be done more often.
And given the influence of environmental conditions on the results, I think it's important. And of course, seasonal trends will dictate it may be wetter or drier according to when you take the measurement. I think Kev was alluding to the fact that if you need to measure under different conditions to understand the performance of the system, not always look at the best possible conditions for the measurement. So I think that says to me that recording the conditions, wet, dry, and temperature alongside the measurement is an important factor. So you can add that into your interpretation of the trend. But I think it is important you actually record it and you trend the analysis. But then the final point would be recognizing how many of these measurements you're going to practically need to do. It is not always feasible to measure them at the same time anyway. Though I do see, for comparison purposes, I can understand the desire to measure apples with apples or compare apples with apples. So
got one to throw out at you as well. One of the questions says that IR compromises the field surge protection installation installed in the field. The field lightning arresters will lower your insulation resistance value, but it's most important, not the absolute insulation value, but the trend of value is what you're looking for. So if you go from 500 meg and you put arresters in there and you're down at 250 meg, you still have an excellent system. You need to trend that at that point to see where you're staying at. So the absolute value is not as important as the trend. So that's why regular measurements are important.
Amen. Let me make one general comment here. I've been thinking there's so much good information coming from all you people. Why can we not get some people involved in this which write the regulations? Can't we get some FAA people to join? Can't we get some ICAO people to join? Tell them about all the valuable information they're going to see about real life and coming and sitting here for an hour a month and learning about the standards that they're writing. And many times we're ignored separately. Maybe there's more strength in community here. I know we have a standard out here. The FAA's head out for comments. Carl mentioned they give us an opportunity to comment. Well, we've had a standard out, which is a primary standard for over a year. We've commented and we've never had a response. Never had a response. So is there anything we can do to help the information from this group drip down, or they be part of this assembly where we can go back and forth and have a collaborative effort in looking at the future and what's working and what's not working?
I would agree with you, Seward. I think the key issue has been, and it's been a quite traditional, is that when we're looking at the ICAO, we look at the visual aids working group in the ICAO, and they are attendees that are seconded temporarily just to attend, and they come from the National Civil Aviation departments. We look at the IEC, the Technical Commission 97. We look at the standards that are producing, and then where do those people come from? Generally speaking, they are seconded via the suppliers, the AGL suppliers, with commercial interests come into play. So it's a very, very difficult situation to bring everybody together in a coordinated international situation. But I do agree with you. Sadly, those people who are inputting to the regulatory standards are not always directly experts in the particular field, and that's pretty sad, I think. Pretty sad. And this is the way the trend has gone. You know, the days, and Tony will know from his day, visual aids panel, or whatever we wanted to call it in those days, Tony, is that they were people persons like yourself who were passionate about AGL.
Yeah, I'd just say, yes, absolutely. I want to say here to what Stuart is saying, and I was linking that with a slightly earlier comment about what we might have in a future webinar, a session on what's coming next. Well, that is a way, surely, of getting the people who are writing the regulations to participate with us, because are they not the people we invite to come and make a presentation on what is coming next? Some of those committees that Stuart is talking about, could we not get the chairman to come along and say what is coming next in our next circular or so on? Would that make some links?
Hopefully, yes.
I think it's a great suggestion, and we will approach we'll approach the visual aids working group and the FAA, and we'll ask them if they will please join us and give us a short presentation and talk to us about the process of standards development, what's coming, and what they're thinking about for the future. And it might be very useful for them to receive our feedback on that matter to help prioritize what is being done at the end of the day for airports, for the people like yourselves out there. So that's a very good suggestion. So
and that should also include the Technical Committee 97 of the IEC, Robert.
Yeah, yes, absolutely. So I will ask the question. So we're now well over time, so there are more questions there. As for those of you not familiar, the recording of this webinar is put onto the TMS trainingsolutions.com website, so you can see a copy of this webinar and a copy of every previous webinar, which they're getting on for 40 now. So they're covering a range of topics, so you can look back and familiarize yourself with a range of issues. So that's on TMS Training Solutions, all one word, tmstrainingsolutions.com. Recording of the website, you can see all the slides we're presenting and all of the presentation. And we also publish the questions and answers. So if you have any, all your questions that we haven't got round to today, we will put on with the questions and answers on our website, so that hopefully you'll get the answers to your questions. If you don't, you can always contact me directly. I'd like to thank the panel first, Tony, Kevin, for presenting, Tony Smith and Stuart, of course, Keith, Carl and Nick for participating in the panel today. I'd also like to thank Damon and Felicity for arranging the webinar, and I look forward to seeing you all on the 28th of May for another exciting episode, hopefully managing visual aids in the 21st century, looking at how we can take all the information that we're recording. So we're measuring all our measurements, how we can use those to optimize the performance of our visual aids infrastructure. Thank you very much, and I'll see you all in a month's time. Thank you.
Cheers.